Hi, my name is Gaurav and I'll be presenting on spectral estimation. So let's go over the introduction and motivation for spectral estimation. So spectral estimation is a process of estimating the spectral density of a random signal from a sequence of time samples of the signal. So why do we need to estimate the spectrum? So it turns out that wireless modems or any radio transmitter needs to occupy a restricted bandwidth since the radio medium is scarce. So in these considerations, not only does the effective bandwidth of the signal matters, but also the spectral roll-off. To verify this, the spectrum of the emitted signal needs to be estimated. So other reasons include we can estimate the distortions caused by the channel, such as the frequency selective distortions or the frequency offset in the transmitted signal. So now let's go over a few background information to understand the concepts behind spectral estimation. So a random process yk is said to be Whiteson stationary if its mean does not depend on n, and the autocorrelation function ryy of k depends only on the lag between the two samples and not their absolute value. Also, this autocorrelation function is symmetric in time. So then we see a relationship between the power spectral density and the autocorrelation function through the Wiener-Khinchin theorem, which says that the autocorrelation function and the power spectral density are Fourier transform pairs. So also filtering of a Whiteson stationary process by linear time invariant filter of filter response h of f produces another Whiteson stationary process yk, where the power spectral density of the input and the output are related by this equation here. Another theorem is the Fourier transform correlation theorem. So if we have the Fourier transform of two Whiteson station random process x and y, then the Fourier transform correlation theorem says that the following relationship holds. So basically what this is saying is that the random complex amplitudes x and y are uncorrelated at different frequencies and have a power that is proportional to the power spectral density of the random process. So let's look at the non-parametric spectral estimation techniques. So in which there are no constraints imposed on the possible form of the power spectral density. And the motivation for non-parametric spectral estimation is the Fourier transform correlation theorem that we saw in the previous slide, which states that the Fourier transform at different frequency are uncorrelated, while its magnitude squared is proportional to the power spectral density function. So let's look at periodogram, which is a technique, which is a non-parametric spectral estimation technique, and it is defined as a magnitude square of the Fourier transform of finite number of samples. So that is captured in equation 3. So the periodogram can also be interpreted as follows, wherein the sequence yk is interpreted to be filtered by a filter that has an impulse response h naught k, where h naught k is a modulated rectangular window that has the following form and has a frequency response as follows. So now let's look at the mean and variance of the periodogram. So the expected value of the periodogram can be found to be the convolution between a window known as the Bartlett window and the power spectral density function, where the Bartlett window is defined as given in equation 7. So now that the convolution between the Bartlett window and the power spectral density function does not yield the power spectral density function itself, the periodogram is a biased estimator. However, as n tends to infinity, one can show that the periodogram becomes unbiased. So the variance of the periodogram can be estimated using the following equation, wherein it can be shown that it is greater than or equal to the square of the periodogram, the square of the power spectral density function, which is independent of the record length n, hence making it an unreliable estimator, because if we have enough number of data, if we have large number of data, that does not decrease the variance. Another problem associated with periodogram is the spectral leakage. So this is the frequency response of the rectangular window, and we see the presence of strong side lobes, which has non-zero contributions at frequency where the power spectral density has no contribution. So this phenomena is called spectral leakage, And in order to reduce spectral leakage, it is advantageous to replace the rectangular window with another window that shows less discontinuities near the edges. So one way to address the bias issue in periodogram is to pre-whiten the data. So if we have some a priori idea about the power spectral density, so we can then design a filter A of f, that whitens the data yk to give xk, and then we can determine the periodogram of the filtered data xx hat of f, where the bias is small since xk is a uh, white and stationary process. So in order to address the high variance of periodogram, we try to average periodogram over k independent data records of length L, and this is known as the average periodogram. So, and the average periodogram takes this form. And the advantage in average periodogram is that the variance is decreased by a factor k. So this brings us to the Blackman-Tukey spectral estimator, which is yet another non-parametric spectral estimator. So the poor performance of the periodogram may be illustrated by considering the following equivalent form of the periodogram. So this is the original form that we had, but with some mathematical manipulation, one can show that the following, it can be broken down into the following equation, where the term 1 over n summation over n yn plus k times yn can be considered to be a crude estimator of the autocorrelation function itself. So the mean of the autocorrelation function estimated above uh, has a bias and variance that increases linearly with the lag k. So this motivated Blackman and Tukey to introduce a weighting sequence WK that reflects the quality of the autocorrelation ACF estimates that decreases with the lag k. So this leads to the Blackman-Tukey estimator, which is given in this equation, where WK is the windowed sequence that has a length less than n minus 1 and has the following properties. So the advantage in Blackman-Tukey estimator is that the variance is now made to depend on n, which was not the case in the periodogram. And this also means that if you have enough data, the variance, we can have a pretty low variance estimator. Now let's look at a few parametric spectral estimation techniques. The generic model considered here is depicted in this figure, where the white noise drives the LTI causal and relational system. So in that case, due to the Whiteson stationarity of the input, this will also mean that the output YK is also Whiteson stationary, that has a power spectral density of this form. So now let's look at an autoregressive process. An autoregressive process of order n is obtained by taking an nth order all pole transfer function that has the following form. The input-output relationship in the z domain can be given by this equation. Now, if we look at the time domain equation of the above z transform, we get the following equation, which justifies the name autoregression because it's a linear combination of its past samples. So from the expression of the power spectral density, we can get the following relationship. And if we look at the time domain expression of equation 18, we get what are called as the Yule-Walker's equation that take the following form, where the matrix, where this matrix is called the covariance matrix, which gets multiplied by a vector of the filter coefficient, and we have the variance of the white noise present as on the right hand side. And this this has n plus 1 linear equation, and we have to solve for n plus 1 unknowns that are present. So now let's consider let's look at the problem of linear prediction. So consider predicting the sample yk linearly from n previous samples. So what we do is we form the prediction as a linear combination of the form that is depicted in equation 20. So the goal now is to minimize the forward error fnk between yk and yk hat using linear minimum mean squared error technique. So it turns out that in order to solve the above optimization problem, we construct what are known as normal equations, which take the same form as Yule-Walker equation that we saw in the previous slide. So this is the form of the normal equation, and there is a faster way to solve this n plus 1 equation known as the Levinson algorithm that exploits the two-pleatsness property of the covariance matrix. So now let's look at autoregressive modeling via linear prediction. The prediction variance in the linear prediction is a non-decreasing function of n. That is, the linear prediction variance decreases as n increases. So the infinite order prediction f infinity comma k is a white noise process, and assume now that for certain order n, we get as close as possible to the white noise process here. So the auto-regressive modeling operation consists in considering the fnk to be exactly white with a variance sigma square fn. So this implies that the power spectral density of the signal yk, the power spectral density of the signal yk can be approximated by the inverse magnitude squared of the Fourier transform of the prediction filter that we have in hand here. So this this is the equation at hand, and this particular method is called as the autocorrelation method, wherein we try to determine sigma fn square and the filter coefficients by solving the Yule-Walker equation, and hence using that to estimate the periodogram of the signal, sorry, the power spectral density of the signal. So here are a few simulation results. So this is a simulation result of this is showing the performance of a periodogram, trying to estimate the spectrum of a colored noise that has a true spectrum represented by the red curve, and the periodogram, as you can see, is quite noisy and has severe spectral leakage in its neighboring bands. And if you look at the performance of the average periodogram, we get a smoother curve, and the spectral leakage also is kind of reduced in this case. So the Blackman-Tukey estimator does a pretty good job in estimating, I mean, in accurately estimating the spectrum of the colored noise. As you can see, the blue and the red lines almost coincide with each other. So the plot at the bottom here shows the performance of parametric spectral estimation technique trying to estimate uh, the spectrum of two tones that are at 0.1 hertz and 0.3 hertz. As you can see, we get a pretty smooth curve and there are no spectral leakage. Thank you.